Hi, Introduction to Mechatronics. My name is Martin-Pilkington. I'm age 22. I'm on a course of Manufacturing and Mechatronics, HNC. You can visit my YouTube on this link, Simon Martin-Pilkington. My interests are jazz, fishing and manga art. My favourites is the game Halo CE. My food is free from brownies, and the place I like to go is River Valley. What I don't like is slow internet speed. Applications and innovation. I did some research about manufacturing processes. During the research, I was looking for high-risk procedures. I found toxins and injuries were two main problems, so my project was focused on these points. I also included reducing costs and prototyping. To summarize, my project at this point is toxic materials, protection from atomic waste, reducing injuries which would be physical, reducing costs in prototype by different methodologies. From the information and my interests, looking at the list and application as well as these innovations, my project would include environmental impact, improve on safety standards, and reduction of costs and resources. Planning. I gathered resources together and I wanted to include robotics in the project. Planning is the most important part of the project. Essentials are timetables, Gantt charts, notebook, good PC software, research, budgets, support, logistics. An outline plan will include individual plans for different stages. Development. In my projects, I wanted to include magnetics. They have always interested me. I did some research and I found that the strongest magnets I could buy are neodymium. In my research, I became interested in electromagnetics and the effects of the magnets on copper. Components. After planning, I put together a list of components I needed for my project. I wanted to include magnetics and a robotic arm. Also, a list of non-component parts, for example, tools, machinery, sundries, PC softwares, workspace. This would further expand as the project grew. Costing. I researched the components I needed for my project. I set myself a budget. I used my own money to fund the project. This all changed when I found I could produce the model in 3D software. Below is an example of my costings. Hello, one of my projects is a magnetic raft. I'm going to show you the software I used during this process. This program is free on the Microsoft Store and it is an app that you can easily use and it's quick and simple. Anyone can use it. You don't have to be technically minded to use it. It's that simple. But from here, we used this app and used it in converting all the measurements from the raft. To see this process, visit the link. Then I'll use CAD. AutoCAD has numerous applications in a wide range of fields. The program can be used for simple projects such as graphs or presentations, or even complex designs. Some other practical applications may include interior designs, aeronautical designs, maps, and architectural designs. To see how this is done, please follow the link. Then SolidWorks. This is the raft, the bottom parts of the raft, where the electromagnetics will pass through on the inside. As you can see from here, I built it in SolidWorks using minimal tree features, which you can see on the left side. But what this software can do is amazing. From here I can then go to simulation and test it, put it through a series of tests such as static and frequency, and from there I will get my results and see if the model is strong enough for what the task it will be used for, and then it will move on to manufacturing. This is the model I 3D printed in resin. Prototyping using 3D printers. Bebo 3D printer. This is the final process for this prototype test model. On the right is the PLA draft model. It can be modified in the slicing software to improve the print quality. Dremel 3D printer. This is the final process for this prototype test model. On the right is the Eco ABS draft model. It is better with the quality and much stronger compared to PLA. However, it is more expensive. Eagle Mars 3D resin printer. This is the final process for this prototype test model. On the right is the grey resin draft model. It is better with the quality and ideal for hobby model making. Go to my YouTube channel for more information. Hello, this is my model. I built this using Microsoft's 3D Builder. This model shows the automation on today's industry. I'm now going to break this down into components to show the mechanical side of the model. This is the robotic arm. It will start the process by picking up the barrel and putting it onto the conveyor belt. This is a cage that protects the motor from the barrel. This is a motorized conveyor. I had a bit of fun here when I was recording this. This is a hydraulic ram. It adjusts the height of the conveyor belt. This is a hydraulic master cylinder. And this is the mechanism to the master cylinder. This is a conveyor, it has rollers and uses gravity. This is an automated mechanism. The first stage, the barrel is caught into the cage. The cage would then slide along the cylinders. This is done via a chain. This is the framework. And now this is the tilt mechanism. It tilts the basket 20 degrees. This is the levitating raft. It levitates by magnets. How this works I'm going to demonstrate later on the next page. This also includes electromagnetics, which I'll talk about later. This is the electronics of my model. So the first one is the robotic circuitry for the arm. As you can see, I've given you a side view of the arm and a circuit that is exploded view of what's inside. It contains a USB PCB assembly board and the input voltage is 6 volts. It has 5 motors and 1 light, all connected to the board, and the PCB board is connected via USB to the computer, where it is controlled by software. So what we're looking now is the conveyor circuit. We have an input of 12 volts which is connected to a switch, which is then connected to the 50k potentiometer, and then it goes to the 10k resistor and then the P55N. And then we have the voltage meter to measure the voltage output. And then the output range would be 1 volt to 12 volts because the motor has a high end of 12 volts. This is the levitating raft RC control circuit. It is controlled by Bluetooth using a phone app. As you can see, it has a HC05 Bluetooth module. The input power is 9 volts using a battery, which is connected to the main board, which is the Arduino Uno R3, and then from there it is connected to the motor, which will turn the doors on the raft. This is the electromagnetic circuit for the raft. It has an input of 12 volts, and then from there it's connected to a switch. After the switch is connected to a potentiometer, that is 50k, and then from there it joins to a resistor, that is 10k. After that it is connected to a P55N module, and then from there to an AC voltmeter, and then going to the output. The output is a variable output of 6 volts, but can range from 1 to 12. I have included a temperature gauge on this circuit to monitor the heat on the copper. Here we have 3 motor mechanism circuits. These control the mechanical sliding basket mechanism and the tilting mechanism. On these circuits, they are very similar to the electromagnetic raft. You have the Arduino Uno R3 board that is powered by a 9 volt battery. The board is connected to the HC05 Bluetooth, and then this controls the motors via PC. I wanted to include magnets in my projects. I did some research. From my findings, I became interested in levitating and superconductive magnets. This is the raft. As you can see, the raft uses neodymium magnets. You can see the red part is the door with 2 magnets on, and then you've got the sides which have 8 magnets like little fins, and then on the bottom you have these 2 big grey blocks. These are where the electromagnetic balls go through. This is what stabilizes the raft. The sides keep it level because it's a top heavy raft, as you can see, because where the barrel sits is right at the top on the barrel catcher. So as we pan around now to the back, you've got the other door and the other side, and if you can see the arm that's sticking right next to the door, the white object, that's it, and that will connect to a motor on the inside. Now as we pan down, you can see directly inside the grey objects, and you've got 2 on the top, 2 on the sides, and then on the bottom bit where we can't see is 2 there, and this will be mirrored on the other side as well. This would then glide between the copper sheets on my model. This is the electromagnetic part of my model. I'm now showing you where the raft would fit. This is an exploded view part of this model. We're now going to start from the bottom of the model and work our way up. You've got the positive wire, the stands, the negative wire which is connected to the resistors, and then you've got the copper which is wrapped around the nails. Then the metal balls sit on the copper wire. This amplifies the magnetic force. Then you have a copper sheet, a resistance sheet, and then another copper sheet, and then the magnetic raft would sit on top. This is now the prototype of a raft we printed in resin. I wanted to mention other PC softwares in this presentation. I found these programs to be important. Here is a list. Blender. It's a free open source animation and modeling software. CyberLink is a pro editing software. MusicMaker. I use this to orchestrate my soundtrack. Sciences of Mechatronics. This graph here, as you see, is a spectrum. You've got from one end on the left your computer to the other end on your right, which is gamma rays. As you can see in the yellow box, it is the ionized radiation. That is the radiation that's really harmful to you in small quantities. But on your left you've got the non-ionizing radiation. Moving on to the next image. This is a table that shows you the AC currents in electromagnetic circuits. The reason behind my research on this is, as you can see in the last section of the table where you've got full wave phase 3, on the right hand side at the bottom is a line, a blue line, that indicates a continuous current, which is what I want in my electromagnetic circuits, than rather it being alternating. This next image you see is a graph of AutoCAD software specifications in computers over time. You can see on your right it's the RAM in gigabytes, and on the bottom is the time in years. As we go across the beginning, which is 2017 on this graph, and go across to 2018, you can see it's 4 gigabytes. If we go further down, which is to 2019 to 2020, there's a huge jump between gigs where you're required to have a computer that can capably run at 16 gigs or 8. This is because of all the features that keeps getting added over time and all the updates. And lastly, the circuit. One of the main circuitries in the model, which is the raft, I'm using the software Fritzing to construct my circuits to give me a visual sight on how and what I can do to them.